Welcome to Topic 7, Lecture 1 of the Data Management module, where we'll be looking at some of the phenomena that can occur when we consider concurrency control with database management systems. In the last topic, we considered in detail the four properties, the so-called ACID properties of a transaction that must be preserved by our database management system. Firstly, to ensure logging and recoverability, which we covered in the previous topic, and secondly, to ensure that we can interleave our transactions. This is to ensure maximum throughput and best CPU utilization in our database management system. So our DBMS is going to have a mechanism to ensure concurrency control, to ensure that the C and the I properties are always maintained. That's the consistency and the isolation properties. That is a mechanism to enable multiple concurrent transactions to safely access the same data at the same time. In this lecture, we're going to look in detail at three phenomena that can occur in the absence of concurrency control. And then as we introduce during later lectures in this lecture, three different approaches to concurrency control, three different algorithms, we will see how these phenomena can be avoided. These three phenomena are called the lost update problem, the uncommitted dependency problem, and the inconsistent analysis problem. We use these three phenomena as a benchmark for our three approaches to concurrency control. We will show that each of the three approaches avoids these three phenomena, and by doing so, it can be proven that these three approaches ensure that multiple concurrent transactions can safely access the same data at the same time, thus ensuring that the consistency and the isolation properties of the transaction are preserved. So let's consider each of these three phenomena in turn. We will first consider the lost update problem. This slide shows what is commonly called a schedule. In this particular case, we have two transactions, TA and TB, that have been interleaved in some way. Time is increasing from the top to the bottom of the schedule. And so this shows the chronological order of each of the operations within the transactions TA and TB. R is a record, and this is a fairly generic term for a record at the logical layer. So in terms of the relational model, you might want to consider the record as being a row of data in a particular table. Our examples assume the existence of a read statement to read a record from the database and a write statement to write a record back to the database. We're also going to assume that a record must be read before it can be written. So if you want to consider this as being analogous to SQL statements, the read would be a select statement and the write would be an update statement. So let's consider the two transactions in isolation first. So remember that we want to preserve the isolation property of transactions. So from the user perspective, so some application running one or other of these transactions, they want the transaction to run as if there are no other transactions running at the same time on the database. So the operation here is quite simple, that each of these transactions is reading the record, and let's assume here that the record has an integer, a tuple with an integer in it, with some value, and we're going to multiply it by 2, and we're going to write the record back out again. And each of the transactions is wanting to do the same thing. But in this example, the two transactions have been interleaved in the way shown, and TA reads a record from the database, modifies it, and writes it back to the database. But because TB is running concurrently, it's reading the same record before TA has written it, and it itself modifies that record. When the modified record from TB is written back to the database, the modification of TA is therefore overwritten, and so the effect of TA's update is lost. If the isolation property of these transactions were maintained, what would happen is that we would consider TA as having run first and then TB, or vice versa. And in that particular case, the final value of the record R would have been 8 to reflect both updates. So that would have been TA followed by TB, or TB followed by T. So if we consider the interleaving as indicated in this schedule, what actually happens, again, assuming that R originally contains the value 2, it will be multiplied by 2 in transaction A, but it hasn't been written yet. So when that record is read by transaction B, it will read 2, and again multiply that by 2 to give 4. And when transaction A writes that record, it will write 4. But when transaction B will write that record, it will also write 4, because it has missed the update from transaction A. So this is an illustration of what we term the lost update problem. So now let's consider the second of our 3 phenomena, the uncommitted dependency problem. As before, we've got 2 transactions, TA and TB, that are operating on some record R that we're going to assume that is a tuple containing a single integer value. And as before, TA is reading that record R, doing some sort of operation on it, in this case multiplying it by 2 and writing it back. We can see that TB does not read the record until after TA has written it. Now some error condition occurs during TA between this point in the schedule and this point in the schedule that causes a rollback. It doesn't matter what that error condition is for the discussion of this phenomena, but what happens as part of the rollback, as we've seen in the previous topic, the database will be restored to its state at the beginning of TA. So record R will revert to the value of R as it was at the beginning of transaction A. So we can see here that transaction B is reading the value of R that is not going to persist because it's going to be rolled back by transaction A that has already changed that record. We can also consider the scenario if TB, after doing the read R, went on to update R before the rollback in TA, then that update would be lost as a result of the rollback. So let's illustrate the uncommitted dependency problem by considering the scenario where R originally contains the value 2. If these 2 transactions had ran in isolation, for instance, TA followed by TB, or TB followed by TA, we can see that the final value of the record R would be 2. And additionally, TB, which successfully completes, would have read the correct value, R equals 2. If we consider the schedule as shown here, again assuming that R originally contains the value 2, with the statements ordered as shown, TB will incorrectly read the value 4. Now, reading uncommitted data in this way is also sometimes called a dirty read. And you will see that in some of the textbooks and literature. Where you see that, you can consider it as being the same as the uncommitted dependency problem. So let's now consider the last of our 3 phenomena, which is called the inconsistent analysis problem. So again, we have 2 transactions, transaction A and transaction B. In this particular case, we're considering 2 records, R1 and R2, which we're going to consider again both as being tuples containing a single integer value. You could consider this problem in the context of the banking scenario that we talked about when we discussed transactions in the last topic. That's where we were transferring some money from one bank account to another. So we could consider record R1 as being the balance of the source bank account and record R2 as being the balance of the destination bank account. We could consider transaction A as summing the balances of the 2 bank accounts